Okay, this question is the hardest one on this paper to get full marks on, I think. But that's because of part C. Part A is a straightforward integrating factor. So we've got nothing in front of our dy by dx. We've got a 2 in front of our y. It's a plus 2. So the integrating factor is the integral of that plus 2 and then e to the power of that. So here we go. To integrate that, e to the power of the answer. So this is e to the power of 2x. Okay, so that means we're going to be multiplying the whole equation through by 2x, so e to the 2x. So for this bit here, it's just going to make that e to the minus 2x vanish. So I'm going to get 2x minus 2. You can leave 2 outside the bracket if you want to. And then I'm going to get 4. That's multiplied by the e to the 2x. So that's the right-hand side. Okay. The left-hand side is the derivative of y times the integrating factor, which is 2x. That's the magic of the integrating factor. Okay, this is wrong at the moment. Now, some people want to go straight to integral of that dx. I prefer to say what's going on. When you multiply that by the integrating factor, you get the derivative of y e to the 2x. So y e to the 2x itself is the integral of 2x minus 2 plus 4 e to the 2x. Which is not hard to integrate. 2x integrates to x squared minus 2x, and this integrates to divided by the 2, so that's plus 2e to the 2x, and of course we must not forget our plus c, and then we need to find y, so we're going to divide by e to the 2x. So y equals, well, there's this, which is just a 2 when you divide by e to the 2x, and all the rest of it I can just put plus e to the power of minus 2x, and I can shove x squared minus 2x plus c, and I've got the first 4 marks, and there's nothing hard there. Okay, part B is about the horizontal asymptote. So you have to remember that on a graph, asymptotes are about, well, horizontal asymptotes are what happens when x is very, very large or small. So I think we're going to need a sketch graph eventually anyway, so let's do it now. So if I think about the graph of this, we're going to have to explain this properly with limits later. But if I just think about shoving a value of x in that's large, okay, if it's large and positive, okay, e to the power of a large positive number is just tiny, and it overwhelms all of what's in the bracket. So for large positive x, I'm going to be close to y equals 2. So the asymptote is going to be y equals 2, because when I'm over here, for large positive values, I'm going to be close to this. So I'm going to state my asymptote is y equals 2. I'll state that at the end. That's only 1 mark. Okay. While we're talking about large values of x, I'm going to be interested probably eventually in whether I'm above or below the asymptote. Well, this is positive when x is very large and positive. E to the power of a large negative value is a very, very small positive value, and x squared is always positive and will overwhelm the 2x and the plus c for large positive x. So I know the graph is going to do this. It's going to be a little bit above the 2 plus a small positive number. Now when x is large and negative, this is still going to go positive because x squared is still positive and will overwhelm these. But e to the power of minus 2x when x is large and negative will be huge because it will be e to a large positive power. So for negative values, the graph's going to go up there. Okay. So anyway, my asymptote is going to be y equals 2, but the justification for that has to be discussing what happens as x tends to. So large positive x means that x is tending to infinity. So now we're using the language of limits. Okay, so I need to think about the limit of, well, 2 doesn't have x's in, so I don't need to consider that one. I need to think about x squared e to the power of minus 2x. I need to think about minus 2x e to the power of minus 2x. And I need to think about c times e to the power of minus 2x. Well, the last one, because it's just e to the power, I know that e to the power of minus 2x tends to 0. The other two, the x squared is trying to go to infinity, as x goes to infinity, but the e to the minus 2x is going to 0. So I need to justify which one I think wins. And there's this standard limit that we know that x to the power of something positive times e to the power of a negative multiple of x, in this case it's minus 2x, this tends to 0 as x tends to infinity. That's one of those 2 standard types of limit that you need to learn and quote. So y equals 2 being the asymptote will get you one of the marks, but to get both marks you need this justification in terms of limits. Okay, on to the nastiest part, which is part C. Now part C talks about, okay, where are we? The line y equals k intersecting the curve in 3 distinct points. Okay, so what does y equals k look like? Well, y equals 2 was this horizontal line here. Y equals k is going to be another horizontal line. And I can see that if that horizontal line is high enough up, it's only going to intersect the curve over here somewhere. And if the horizontal line is a long way down, okay, then it's probably going to miss the curve completely. What I need to know is think about the behavior of the curve in terms of the way it joins these up. Now, the one thing it can't do, implied by the question, is it can't just slope smoothly down and just slope down all the way until it joins this, because then any horizontal line would only cut it once. It's going to have to go back on itself. In other words, it's going to have to come down, have a minimum, go up again, have another stationary point, I mean possibly more than 2, but it's going to have stationary points. And part C, to get started on it, well, we need to look at stationary points. I say to get started on it, actually, that's not true. It is the trickiest part of the question, but there are 2 easy marks at the beginning, because the first thing we're told is that we have this point on the graph. So even if you don't understand what this stuff is about with the 3 distinct points, you know that you've been given an x and you're given a y, and you've got the general solution, so we can sub these in and find c. So that's the bit you're expecting to have to do. So we'll come back to the 3 intersections, and let's just put x equals -1 and y equals 2 plus 4e squared into this equation and see what we can do. So y is 2 plus 4e squared plus e to the power of -2x. X is -1, so this is e squared. I'm putting -1 into this. -1 squared is 1 plus 2 plus c. And in order to find out what c is, I can see that this 2 agrees with that, and that 4e squared will agree with this as long as c equals 1. So now I know that c equals 1, then this equation with c equals 1 there is the equation that I want. So here is the particular solution that I'm interested in. So now I need to know the values of the horizontal line that could intersect this 3 times, which means I need to know about the wiggliness of this graph. I need to know about its stationary points. So I'm going to need dy by dx to equal 0. So stationary point, dy by dx equals 0. So one way to do this, the obvious way, is to differentiate this. I'm going to need to use the product rule on this, set it equal to 0 and solve the equation. Okay, but I could, just as an alternative way to do this, just so you've seen it happen, I could substitute dy by dx equals 0 into the original differential equation. Because if I've got dy by dx equals 0 and I've got y in terms of x, I can substitute those 2 things in, and then I can solve what I get in terms of x. So I'm using the dy by dx equals 0 instantly, and I'm not having to do any differentiation. So it's very slightly quicker. So if I do that, the equation says dy by dx plus 2y. So dy by dx is 0, because I want a stationary point, and 2y is, well, I've got my function for y. Found my constant, so this is 2 plus e to the minus 2x times x squared minus 2x plus 1. And that has to equal the right-hand side of the differential equation, which was 2 brackets e to the x minus 1, e to the minus 2x plus 4. So that's what the differential equation looks like when we put 0 in for dy by dx and our formula for y in for the y. And now I've just got to solve this for x. So multiplying this out, I see that I'm going to have a 4, which is going to equal this 4, so that's nice. And I can see I've got a factor of e to the minus 2x, and I've got a factor of e to the minus 2x here. Now, e to the minus 2x can't equal 0, so it is legitimate to divide both sides by that. Otherwise, you'd need to get everything on one side and use it as a factor. So what the things that are left are equal. I mustn't forget this is 2 times x squared minus 2x plus 1. So that's 2x squared minus 4x plus 2 equals 2x minus 2. which simplifies to this quadratic with these solutions. So these are the x coordinates where I have stationary points, where dy by dx equals 0. Okay, so I need to know the y coordinates that go with these. So when x equals 1, y equals, substitute 1 into this equation. And because 1 minus 2 plus 1, this bracket when you put 1 into it, is 0, y just equals 2. So I've got the point 1, 2. And the other stationary point is going to be when x equals 2. Sub that in. Okay, here's what we get. And 4 minus 4 plus 1, oh, that's 1 this time. So we get 2 plus e to the power of minus 4. So I've got the point 2, 2 plus e to the minus 4. So those are my two stationary points. Okay, so let's try and put them on the graph. So the first one had a y coordinate of 2 and the second one had a y coordinate of 2 and a bit. So on the graph here, at x equals 1 and x equals 1 and x equals 2, the 2 is actually on the asymptote. Okay, so then don't let anyone ever tell you that curves never touch their asymptotes. This one actually has the asymptote as a tangent there, has another stationary point at 2, and then it's got to tend towards its asymptote. Okay, so the only way I could draw that, and having a stationary point here, okay, and still have y equals 2 as the asymptote, is by having a minimum point here and a maximum point there. Okay, it's the only way of doing it with exactly two stationary points. If you try to use anything else, then you can't actually get back from the level of 2 here to this. So I've used a graphical argument there to say that there's a maximum at 1, 2. Now, the mark scheme for this question has all kinds of rubbish using the second derivatives. Okay, I think you do have to probably think about the graph, and the graph is enough to show that this is a minimum point. Do I say maximum before it's minimum? And this is a maximum point. That's quite clear from my graph. So that's all the justification you actually need. If you sketch the graph, which you kind of need to visualize anyway to see how the k business works. Okay, so this has got a y coordinate of 2 and a bit. It was 2 plus e to the minus 4. This has got a y coordinate of 2. So the values of the positions of this line have to be in between the y value there and the y value there. In other words, they have to be in between these two y coordinates, and they're not allowed to equal those, because if they equaled either of those, I'd have a tangent. So for example, the asymptote, okay, only intersects it once, and the tangent here would intersect it twice, once there and once there. So it's got to be a strict inequality. So we're going to say that therefore 2 is less than k is less than 2 plus e to the minus 4, and that will get us full marks.